Hi, thanks for tuning in. I'm Ainesh Bakshi, and my co-author Hijia and I will be talking about our result, robustly learning mixtures of K arbitrary Gaussians. This is joint work with Ilias Diakonikolas, Daniel Kane, Pravesh Kothari, and Santosh Vempala. This talk will be divided into two parts. In the first part, I'll describe the problem and the context, and provide a formal statement of our main results. In the second part, Kay will take over and describe some technical ideas we introduced in this work. Let me begin by defining the problem of learning a mixture of K-Gaussians. Here we consider a mixture denoted by M, where each Gaussian is parameterized by its mean mu I and its covariance sigma I. Additionally, we have K non-negative mixing weights denoted by W sub I that sum to 1. Then we are given as input a set of n samples from this mixture using the following random process. We pick the jth sample by selecting Gaussian I with probability Wi, and then sampling x sub j IID from the Gaussian with mean mu sub I and covariance sigma sub I. The picture to keep in mind is as follows. We see an unlabeled set of points from the mixture. Here I've color-coded the points depending on what component they were drawn from. But note in general, two Gaussians can be almost completely overlapping, such as C1 and C2 in this picture, and we cannot always recover the coloring. Therefore, our goal will be to output a mixture of K Gaussians, which is denoted by M hat, and parameterized by the mixing weights W sub I hat, the K means mu sub I hat, and the K covariance is sigma sub I hat, such that M hat is close to M. In particular, the notion of closeness that we will require is that M is close to M hat in total variation distance. Recall, the total variation distance between two distributions is denoted by half of the integral over x of the absolute difference between px and qx. We require the output to be close in total variation distance since this notion captures overlap between probability distributions. Also, if we make no assumptions on the input, in particular, we don't even assume that each component is distinct, then total variation closeness between the two mixtures is the best kind of guarantee that we can hope for. Later in the talk, I'll describe our techniques can even recover stronger parameter estimation guarantees whenever it is statistically possible to do so. Okay, so this slide is the entire problem setup in the non-robust setting. Let me now discuss some prior work on the non-robust version of learning Gaussian mixtures. This problem has a rich history in theoretical computer science and theoretical machine learning, dating back to the work of Dasgupta in 1999. The initial set of algorithms learned the mixture when each pairwise mean was well separated. Next, in around 2008, Brubaker and Vempala gave an algorithm to learn the mixture when the means or the covariances were separated. Finally, in a set of breakthrough works by Kalai Moitravelliant, and Belkin and Sinha in 2010, gave algorithms to learn the arbitrary mixture of Gaussians problem. That is, solve the problem that I mentioned on the previous slide without any assumptions on the input. These results are based on exploiting the algebraic structure of the problem, and in particular, exploiting the polynomial relationship between Gaussian moments. As the title of the talk suggests, we are interested in a robust variant of the mixture of Gaussians problem. In particular, we consider the robust statistical model initiated by works of Tukey and Huber back in the 60s. This model asks for estimates that are robust to a small fraction of the data being arbitrarily contaminated. The model aims to capture systematic error in data collection and potentially nasty outliers. This has been an active area for research in the statistics community, spanning multiple decades, as evidenced by multiple books that have been dedicated to designing robust estimators. However, typically the estimators that are obtained in these works are computationally intractable in high dimensions. This brings us to the central motivating question of our work, which is whether there exists an efficient algorithm for robustly learning a mixture of K Gaussians in the presence of adversarial outliers. This question has come up in several prior works on algorithmic robust statistics, and it also was highlighted as the central open question in the Foundations of Data Science program at the Simons Institute in fall 2018, where I first came across this problem. Okay, now let me briefly mention prior work on designing robust estimators for learning Gaussian mixtures. In recent work in 2020, Ashtiani et al. Obtained tight sample complexity bounds for learning Gaussian mixtures. However, the corresponding algorithm is not efficient. In the context of efficient algorithm design, several special cases have been considered, starting with the breakthrough works for estimating the mean and covariance for a single Gaussian in polynomial time, which was discovered concurrently by Diakonikolas, Kane, Lee, Moitra, and Stewart, and Lyra and Vempala in 2016. Next, in 2018, Hopkins, Lee, Kothari, Steinhardt, and Diakonikolas, Kane, and Stewart simultaneously came up with an algorithm that handled the setting where the means were separated for a mixture of K-Gaussians. Building up on this line of work, in 2020, we obtained an algorithm for learning non-spherical mixtures that were separated either by mean or by covariance. And this was joint work with Pravesh Kothari. Concurrently, Diakonikolas, Hopkins, Kane, and Kamarkar also came up with a similar result. Right? In 2021, Kane considered the case of learning a mixture of two equiweighted Gaussians without any separation assumptions. And Louis and Moitra extended this to the setting of K components, but with bounds on the mixing weight and the variance of each component. With that context in mind, let me give an informal statement of our result. The first theorem that we obtained says that given a contaminated sample from an arbitrary mixture of K-Gaussians, there is an efficient algorithm that recovers a mixture close to the uncorrupted input in total variation distance. Note that this statement works without any assumption on the input and completely resolves the central open question I mentioned a few slides ago. The second theorem that we prove is a similar statement, where in addition, we can recover the parameters of the input, that is the mixing weights, the means, and the covariances, whenever it is information theoretically possible to do so. Next, I'll formalize the robustness model that we work in and provide a formal statement for our results. So as before, let M be an arbitrary mixture of K-Gaussians parameterized by the means, mu sub I, covariances, sigma sub I, and mixing weights, W sub I. Now, an adversary comes along and designs a distribution that is epsilon close to this distribution M in total variation distance. This distribution can be adversarially chosen with respect to the input distribution M and the algorithm that we design. The adversary then samples n points from this corrupted distribution, denoted by y1 to yn, and this is the set of points that is given to us as input. Our goal is to still output a mixture, which denoted by m hat, that is close to the input mixture in total variation distance. So formally, our first result states that given an epsilon corrupted sample of n points from KGMMM, sampled from the adversarial model as described in the previous slide, there exists an algorithm that recovers another mixture of K-Gaussians denoted by m hat, which satisfies the following. So with probability at least 99%, now the total variation distance between m and m hat is bounded by a function of epsilon. In particular, it is at most epsilon to the 1 over k to the k squared. The number of samples required by our algorithm are d to the k times poly sub k of 1 over epsilon, where the poly sub k suppresses a k to the k squared dependence. The running time is n to the O of 1, so a fixed polynomial in the number of samples, times poly sub k of 1 over epsilon, which again hides this doubly exponential and k dependence. We also note that while there is room to improve the epsilon dependence in this theorem, the dependence on d and k in the sample complexity is tight. In particular, this result of Diakonikolas, Kane, and Stewart from 2018 shows a statistical query lower bound of d to the omega k for the number of samples required to solve this problem. We also note that our algorithm improves the running time of the best known non-robust algorithm for this problem, which obtains a doubly exponential in k dependence on the dimension, whereas we obtain an algorithm that runs in d to the k time. Okay, let me next describe the setup under which we can recover the parameters of each component in the input mixture. So as usual, here we get an epsilon corrupted sample from the mixture M, where the mixture is now a statistically learnable mixture of Gaussians. I will define this notion, statistical learnability, formally on the next slide. Note our goal is to still output a mixture of K-Gaussians M hat that is close to the input mixture, but we will require something stronger now. We want that for all I, the total variation distance between the ith component of the mixture that we output and the ith component of the input mixture is not too large. It is also not too hard to show that such a condition implies that we can recover the means and covariances in the relevant notion of parameter distance. We would also like that the estimated WI hats are close to the original input WIs, so we recover the mixing weights as well. Okay, so now let me formalize this notion of statistical learnability. We say a mixture is statistically learnable if for all I different from j, we have that the total variation distance between the ith component and the jth component is at least epsilon. And the mixing weight for each of the components, that is the w sub i's, are also at least epsilon. Note that this notion is a minimal information-theoretic assumption under which we can hope to recover the parameters of each underlying component. To see this, note that an adversary can effectively corrupt the epsilon fraction of the points that differ between any two components if the TV distance between them is less than epsilon. And then the adversary can make these two components indistinguishable. A similar argument holds if the mixing weight W sub I is less than epsilon. The picture to keep in mind here is that a mixture is statistically learnable if for every pair of components, say let's C1 and C2, there is at least an epsilon gap between the set of points that we observe. So if we look at the difference, the set difference between these two sets, this is an epsilon fraction of the total number of points in this component. Okay, so under this condition, our second theorem says if you're given an epsilon corrupted set of samples from a statistically learnable K Gaussian mixed model, we show that there exists an algorithm that recovers K GMM denoted by M hat, such that for all I, the total variation distance between the estimated component, which is n sub mu I hat and sigma I hat, and the input component is bounded by poly sub k of epsilon. The absolute difference between the estimated and true mixing weight is also at most poly sub k of epsilon. The sample complexity and running time is the same as before. With that, I conclude my part of the presentation and hand it over to Hay to discuss the technical overview of our talk.
Next, I'll go into the technical details of our robust learning algorithm. There are two main techniques. The first one is robust partial clustering. This is also the first step of the algorithm. I'll explain what it means. In this step, we'll try to cluster the points into subgroups if they are partially clusterable. Partial means we only do clustering for the pairs of components that are separated, and we keep these components with large overlap in the same subgroups. As shown in this figure, we can see the right components and the y components has a large overlap. So we'll keep them in the same subgroup, and also for the blue, green, and yellow one. But there is a separation between the yellow subgroup and the blue subgroup. So we'll divide them into two parts. And also for each pair of components in the yellow and blue groups, we can see they'll have a large TV distance. So we can separate points with a high probability. And after this step, we divide the mixture into several submixtures so that inside each submixture, the components are close to each other. Then using this additional condition, we can do our second step, robust tensor decomposition. Here we'll learn the means and covariances of non-clusterable submixtures. So combine the two steps, we'll recover fully, so all the parameters of the mixture. Now let's move to the first technique, robust partial clustering. Robust clustering problem of Gaussian mixtures was recently solved by two groups concurrently. The first is by Bakshi, Kothari, and the second group is Diakonikolas, Hopkins, Kane, and Kamaka. Both of them gave a robust clustering algorithm with two assumptions. The first assumption is that the Gaussian mixture is equiveighted. That means always Wi equals to 1 over k. And the second assumption is that the mixture is fully clusterable. So each pair of components is separated in total variation distance. But here we need an algorithm that to solve a general case that we want to solve for arbitrary weights, and also we want to the algorithm works even if only some of the components are separated. Instead of these two works, we also use the sum of square techniques to build our algorithm. And we also use some properties from these works that's, for example, the anti-concentration of Gaussians. The difference is we'll specialize our algorithm to only two types of separation, mean or forbidden separated, not for the TV distance separation. So here from these three figures, we can see if two Gaussians are TV distance separated, they can be one of the three types of separation. The first one is mean separated. So there exists a direction. If we project out points onto this direction, we can still separate points according to, because they have a large mean distance. And the second one is spectrally separated. Similar to the first one, this is also a low dimensional separation. But the difference is if we project points into this spatial direction, we can separate the points by their variance. Here we can see all blue points concentrates around the center, but green points is very small. And last type, the forbidden separation. This is a high dimensional separation. So even if we project to a low dimensional subspace, we can't separate the samples. But in high dimension, we can separate them using this spin shell. And all the red points are inside the shell, but the white points are outside. And in our case, we only focus on the first and the third type of separation, because these are enough for our following steps. And this simplification improves running time and the sample complexity to a poly D and poly 1 over epsilon. And this helps us to make an efficient full algorithm. And next, we move on to the second technique. What should we do for the non-clusterable mixtures? Even in this case, we still can show that we can learn the parameters of the components. We will use the common methods from the history of learning problems, the method of moments. But instead of the conventional moments, we'll use Hermite moments of Gaussians. It's similar to moments, but it has bounded covariance, so we can robustly learn them. To get a better understanding of Hermite moments, let's look at an easier case from K20. So here we assume means are 0, and the fourth order Hermite tensors T4 has the form of this. So it's a linear combination with the weights and the symmetric form of covariances matrix minus identity, cross product covariances minus identity. This is a fourth order tensor, and the symmetric form means we do averaging over all the permutation of the nodes of tensors. And this fourth Hermite moments has very good property. For example, Kane introduced a tensor decomposition method that is, we can take two random unit vectors A and B and apply them to Hermite tensor. As we can see here, if we choose A and B properly, we'll get this form. So it looks like a sum of out covariances minus identity plus low rank errors E. Here E is a matrix of rank order K square. Because K is a constant, so E is a matrix of constant rank. For this, if we have this lemma, this means with enough many trials, we'll find a good A and B so that we can recover out covariances up to a low rank error from the Hermite tensors. But the next question is, what happens if means are not zero? The good thing is we have at most K different means. So all K means lie in a K-dimensional subspace. And we have this lemma says that odd means and low rank terms E lie in the same low dimensional subspace. And we can find this subspace by computing the eigenvalues or singular values of the Hermite tensors. Now we have the subspace and we have the almost correct covariances. So we reduce our problem to a low dimensional robust learning problem. And this problem is easier because we don't need to worry about the error depends on the number of dimensions. So in this case, a modified version of non-robust learning algorithm works. To conclude the second step, this is the theorem for our least recover algorithm. We assume these two conditions. The first one is all the means are bounded by a constant, and second is covariance matrix minus identity are bounded by constants. We have these two guarantees from our first step, the partial clustering. So because partial clustering already do the separation between those with high mean separated or with forbidden separated. So already we got these two guarantees from the first step. And then we can find the subspace of dimension of poly 1 over epsilon that contains all good estimates of means and covariances. And further, as I just mentioned, we can use this subspace to find a list of candidate parameters. And the size of list is only polynomial. So it's possible to select the best one from the list. Finally, we can give our overall algorithm. As we just seen, the first step is to do the robust partial clustering. And after this, we'll have a list of submixtures. Then we can apply the least recover of parameters by robust decomposition on submixtures. And this step will give us a list of candidate parameters. And we know that there exists at least one good parameters that will be close to the true ones. Next, we'll separate the thin components from the our list of parameters. Thin here means that the eigenvalue is small. So one of the eigenvalue of covariance is small. So if we project points into the eigenvectors into the corresponding eigenvector, we can see out points will concentrate over the small interval. And that's what this means. And we'll separate those special cases because we already have our good estimates of parameters. So this can easily done. And the last step, we'll find the closest hypothesis in our list using fresh samples. That's all I've got. Thank you for listening.